Hello friends, welcome back to my channel. So it is day 2 of daily organic practice on name reactions and organic reagents. Today we are going to take aldol condensation. This is very basic type of reaction, but we will take very important points about this reaction because most of the time questions comes from this topic, right? So we will take this one. We will take how we can generate different type of enolates and what is the diastereoselectivity when we are using different type of enolates. So what are the requirements? First requirement is we need a carbonyl having alpha hydrogen with alpha hydrogen, so it can undergo enolization. It will form enol or enolate depending upon the condition. Either we are using base or we are using a acid, right? Second requirement is we need a electrophilic carbon center. These are two requirements of this reaction. So this reaction can be catalyzed under basic condition or under acidic condition. So first we will take basic mechanism using base catalyzed aldol condensation. Then we will take how we can do it under acid catalyzed catalysis, right? I should write here CH3 suppose, and then I will use a base. Suppose I am using NaOH. This base will first remove a proton which is acidic in nature. So this carbon has alpha hydrogen, so one hydrogen can be removed from this process, from this carbon, and we will have negative charge here. Then in next step, this negative charge can come to this position and this will shift here to oxygen. So ultimately it will form a enolate. Now this enolate, first requirement is fulfilled. Now this enolate can attack on another molecule of acetaldehyde or any other electrophilic carbon present in the reaction mixture. So suppose we are taking again acetaldehyde here. So this carbon will attack on this carbon, this bond will shift here. So what you will get here, this O minus will form OH after taking proton from the reaction mixture, which is released from this step, can be accepted by this oxygen to form OH. Then we will have here this CH2 and here we will have this double bond. So this is our aldol formation. Till this step we are generated a aldol. Now depending upon the condition, further reaction will take place. So what are the conditions required for further reaction? Stronger base. If we are using a stronger base in the reaction, then further reaction will proceed. Or we are using high temperature condition, a reaction is taking place for longer time. Higher temperature, longer time, stronger base. All these conditions will lead to the elimination reaction, and this elimination reaction is slightly different. This one is called as E1CB mechanism, elimination 1 on conjugate base, right? So what we need a base which will remove this acidic proton, and when this proton will be removed, I am directly showing it here. We have this one. Now we are using a base. This base will remove this proton, this bond will shift here and this will shift to oxygen. We will get this one. Then in next step, this negative charge will come back, this bond will shift here and OH is removed. So this reaction is entirely different because we are directly removing a OH in an elimination reaction. Most of the time what we do in elimination reaction, we convert OH into H2O, right, and then we will remove it. But in E1CB mechanism we can also remove groups which are not very good leaving. So this is your elimination product. This complete reaction is called aldol condensation reaction. Then we will take a base catalyzed reaction. Suppose we have a cyclic ketone here and we are using acidic condition. So first step is this proton will be attached with this oxygen. This oxygen having lone pair of electron will attack on this proton and it will form this, right? In next step, one proton from this carbon, alpha carbon, you can remove at this state, at this carbon or from this carbon. so this bond will shift here, this will shift here. So what you will get here, we have generated a enol. This is not enolate, it is enol, right? Again we are using the same ketone, so first we have to convert it into more electrophilic in nature. This one is not so much electrophilic, not so much reactive. So if I will attach a proton here, this carbon will become more electrophilic in nature. Now it can easily participate in the reaction. This will attack on this. The lone pair of electron present on oxygen will shift here, this bond will shift here, this carbon will become negatively charged having high electron density. Now it can attack on this carbon, more electrophilic in nature than cyclopentanone. So this bond will shift here. What we will get here, this will first become OH plus, then we can remove this proton and it will become ketonic, it will become C double bond O, right? In next step we will use again proton present in reaction mixture, and this proton will attach with this OH, it will form OH2 plus, right? So now it will be removed and what we will get here are 3-degree carbocation. So one proton will shift here, this bond will shift here, one proton is removed and we will get our elimination product. So reaction mechanism is different than previous one. We are using here elimination reaction mechanism. This is a type of E1 mechanism, right? So it is entirely different than E1CB mechanism. This step is entirely different than base-catalyzed aldol condensation. So be careful about it, right? Then next is, this is very interesting reaction. You can call it as Cross-aldol condensation reaction. So this will tell you that how you can decide which will provide us enolate and which carbon will act as your electrophilic carbon. Here we have CH3, right? Not H, this is CH3. So in this case, this compound cannot provide us enolate because it doesn't have any alpha proton, is not present in it. There is no alpha proton, you can write it as absent. In this case we have a alpha carbon which contains alpha hydrogens, it can provide us alpha proton. So it will provide us, first it will form this, then this bond will shift here, this will shift here. What you will get here, this will be your enolate. Second thing is we have this electrophilic carbon. It is much more electrophilic than this ketone. First point is it is a aldehyde, much more reactive than ketone for the reaction, right? Second point is it is attached with a electron withdrawing group, and this electron withdrawing group is making this carbon more electrophilic in nature, so it can easily participate in the reaction like this, right? Rest part you can do easily. So you need a compound which can act as which can provide us enolate. Second one should act as electrophilic carbonyl center, so it should be electron poor in nature. One more thing is why we are not in this reaction, it is not showing self condensation. Self condensation means why this ketone is not attacking on another molecule of ketone. It can also attack on this, first it will form enolate and then it can attack on second molecule of this ketone and it can show self condensation reaction, but this reaction is less favorable because in this case we have aldehyde which is much more reactive than ketone, right? So this reaction will be preferential. You can also have a small amount of cell condensation product, but major product will be due to cross condensation. Then next is, this next point is very important, that types of enolate, right? So you can have this type of reaction conditions. Now you have to decide that what will act as enolate and which carbonyl will act as your electrophilic center. So in this case we have here nitromethane. This nitromethane can provide us enolate can undergo enolization philic center, so it is very good substrate for cross condensation reaction, and we are using a base here. So this base will first remove a proton from this position, this bond will shift here, this will shift here. So what you will get this type of enolate. Now second point is it will attack on this carbon, right? So you can do the rest reaction very easily. So this is a specific type of enolate. Second one is using this LDA, lithium diisopropylamide. So it will provide us lithium enolates. We can easily do this reaction, but the important point is it will give us kinetic enolate. Kinetic enolate means whenever we have unsymmetrically substituted ketone, then proton or the acidic proton will be removed from the less substituted carbon, right? All things are very easy, but important points to be remembered here, right? So first we will get a enolate like this, proton will be removed from the less substituted carbon, then this will attack on this electrophilic carbon, this bond will shift here, this will shift, and this double bond will shift on oxygen. What we will get here, right? Now this negatively charged oxygen will take proton from this TSOH and it will form OH, right? And rest step is elimination reaction. So what will happen in elimination reaction? This tosylate formed at this stage will remove this proton, this bond will shift here, this will shift on oxygen, and in next step this negative charge will come back, this will shift here, and OH will be removed. So this is lithium enolate, and the lithium enolates are not good for aldehydes, right? Most of the time the reaction will be given for ketones. This is not good for aldehydes. Then third type of enolate which we can generate is Silyl enol ethers, and for this we need a base, and trimethyl silyl chloride is used most of the time. So first step is the use of this base triethylamine. This triethylamine will remove a proton from more substituted carbon. This will give you thermodynamic enolate. In this particular case we have only one option, but when we have unsymmetrically substituted ketones, this will give you thermodynamic enolate, means proton will be removed from more substituted carbon. This is the basic difference between this trimethyl silyl chloride and LDA, right? So first we will have to remove this proton, and we will get a enolate like this. Then it will attack on this trimethyl silyl chloride, and it will form silyl enol ether, this one, right? And in next step we will use our electrophile, this one, and for this reaction we need Lewis acid, and most of the time titanium tetrachloride is used because it is more stable in nature. When it will become more stable means less reactive, so to increase its reactivity we need a Lewis acid. You can write this titanium chloride like this. This oxygen having lone pair of electron will attack on this titanium and Cl will be removed, right? Actually it should be bonded like this, so titanium Cl will be removed, and first it will form this one, right? Now your silyl enol ether will participate in the reaction. The lone pair of electron will shift here, this will shift, and it will attack on this carbon which is more electrophilic in nature after attached with this titanium chloride, and this bond will shift here, right? You will get this product. and in next step the Cl minus released at this stage will attack on silicon atom and this bond will shift here. You will get this one. In next step Cl minus will attack on this titanium and then this bond will shift here on oxygen. It will attach again with this trimethyl silyl group and then you can do its hydrolysis and finally you will get this molecule. Next type of enolate is using this Wittig reaction, right? So I am using here a alpha halo ester and this ester will be first treated with this triphenyl phosphine. So this triphenyl phosphine having lone pair of electron on phosphorus, it will attack on this carbon and Br will be removed. So what we will get here, this one, right? This is your phosphonium ester. Then we will use a base. This base will remove a proton from this carbon, quite acidic in nature because close to electron deficient phosphorus and carbonyl group, right? So we can remove it easily, right? You will get this one. Then in next step I am using a aldehyde. So this bond will shift here, it will shift on this carbon, then it will attack here and this bond will shift. So what we will get here, this is almost similar to your Wittig reaction, right? We will get this one. Then this oxygen will bind with this phosphorus and here we will get oxaphosphatane. Now we know the rest reaction, this bond will shift here, this will shift here because phosphorus has very strong affinity for oxygen. So we will get here, this will be final product, right? This reaction is good for aldehydes, but if I am using a ketone for this reaction, it will not give me a good result. So with ketone, phosphonate stabilized esters are used. So you have to use this phosphonate for this reaction. This will be used in this step, right? And from here you can use a base. This base will remove acidic proton and the rest reaction will be same as this one, right? If I am using a ketone here, this will be used. This is called your phosphonate ester, right? So next is another type of enolate which we can generate using amine, right? So they are called as Aza-enolates. How we can generate them? So first step is I am using a amine with under acidic condition. So first what I need to do, I will attach this proton with this oxygen. So this carbon will become electrophilic in nature, right? Then I will use this base, this amine, it will attack on this carbon, this bond will shift here. So this is the step for generation of Aza-enolate. You will get this one. Now this nitrogen has positive charge, so in next step what I can do, transfer a proton from nitrogen to oxygen, so it will become a good leaving group in nature. This lone pair will shift here and water will be removed. In next step I will use a base, that is LDA. So it will remove proton from this position. These are acidic. You can compare this carbon nitrogen double bond with carbon double bond oxygen, right? So hydrogen present at alpha position are acidic when they are next to carbonyl. Similarly they are also acidic in nature, so we can easily remove them, and when you will remove it, this proton, this bond will shift here, this will shift on nitrogen. So what you will get, this nitrogen will become negatively charged, so it can bind with lithium because we are using here LDA. This is our Aza-enolate, right? We can use this Aza-enolate with the reaction with this aldehyde. The next reaction is very simple. This bond will shift here, this will shift here, and it will attack on this carbon. Next is diastereoselectivity in aldol condensation. What is the meaning of it? Suppose we are using a ketone, this ketone will provide us enolate, right, and this will act as electrophilic center. Now I am using a base, and this base will remove a acidic proton, right, and it will generate a enolate. So when I will treat this enolate with this electrophilic, there are two possibilities that I will get this type of product. The R attached here and OH attached here are on the same side. They can be above the plane or they can be below the plane. One possibility is this one. Second possibility is that I will get a product in which these two are on the opposite side, which is called as anti-product. This one is syn product and this one is anti-product. There are two possibilities, and its formation is through the six-membered transition state. If you want to go in the detail how this transition state is formed, you can watch my video on Carruthers chapter 1. I will provide the link in I button, right? You can watch the detailed video here. Here you can understand it in very brief manner, so you can solve your question during the examination, right? So I will give you only the direct points which you can remember. So it is through six-member transition state, and in six-member transition state these R group should be in equatorial position to provide this structure stability, and when they are in equatorial position you will get thermodynamically stable product, or you can understand it in another way, that you can have thermodynamically stable product or you can have kinetically stable product. You have two possibilities. In thermodynamically stable product you will get anti product as major. This is your thermodynamically stable product. Anti product is thermodynamically stable product, and kinetic product is your syn product, right? Or one more thing is here, when you are generating anti product, it is through trans enolate, means this enolate is in trans form. It will give you anti product and it is thermodynamically stable, and through cis enolate you will get syn product and it is your kinetically stabilized product, right? So remember this point, you can remember only one and do the reverse of that. Then what will happen when different type of reagents are used? You can easily understand by this point that whenever you are using kinetically stabilized product, it is similar to using LDA. In case of LDA we get kinetically stabilized enolates. That is why we are removing proton from the less substituted carbon. And in case of and with weaker bases and high temperature conditions, you will get thermodynamically stable enolate and it will give you anti product, right? So with LDA what are the possibilities? So I am taking here only the ketone which will provide us enolate, right? So if I am using LDA, what are the possibilities? That it will provide me cis enolate. Cis enolate means this O negative and the group attached here are on the same side. This will be called as cis enolate. Second possibility is it will give me trans enolate, like this. This is your trans enolate. Two possibilities are there. This cis enolate will give us syn product when it is treated with another molecule of aldehyde or ketone, and this trans enolate will give us anti product after treating with aldehyde or ketone, right? So when this R is smaller in size, like ethyl group, then it will give us trans enolate as major product. Smaller sized group attached here, it will not show steric hindrance with it. Steric hindrance will not be there. You can easily have trans product which is trans enolate, which is more stable in nature. But if you have bulkier group attached here which is larger in size, like tertiary butyl, you will get cis enolate as major product, because this bulkier group can show steric hindrance with the group attached here. So it will not give you trans-enolate, it will give you cis-enolate. Cis-enolate means your major product will be syn, right? So remember this point also. This is with LDA. Suppose I have a cyclic ketone in the starting, so I have to generate a enolate first. In this cyclic ketone, the only possibility is generation of this type of enolate. We cannot break this ring, so we have this oxygen and this group trans to each other. So I can generate only trans enolate with this cyclic ketone. There is no possibility here. I cannot generate cis enolate with this. And when I will treat it with this aldehyde, what will happen? This bond will shift here. You will get this product. Now question comes that because it is trans in nature, that is why you will get anti-product. Anti-product means if it is below the plane, it will remain above the plane. This carbon bond will remain above the plane. So you will get anti-product, right? Then we can have different type of enolates, and we will see what will be the diastereoselectivity with different type of enolates. So most common is boron compounds, or you can call it boron mediated aldol condensation. So suppose I have again I will have the same type of ketone as we have used in this case. Now I am using boron compounds. So again I can have two type of enolate. I can have this cis enolate, or I can have trans enolate, cis or trans. Now how I can decide that which type of enolate will be formed? So if you have a smaller size ligand attached with boron and they have good leaving group attached with them, right? And in this reaction you also need a base, and suppose this base is bulkier in size like diisopropyl ethylamine, then you will mainly get this cis as major product with smaller ligands, good leaving group and bulkier bases. You will get cis as major product, and this cis enolate will give you syn aldol. And with heavier size ligand, bulkier ligand, poor leaving group like Cl, unhindered bases triethylamine, you will get this trans as major product. What are the conditions? Bulky ligand, poor leaving group and unhindered bases. You will get trans as major product. Remember this point. This is very important, right? You can surely have a question based on this boron enolate. Then one more thing is, if I am using titanium enolate, this titanium enolate can be generated using titanium tetrachloride and a base. It will give me syn aldol. Most of the time it will give me syn aldol. And if I am using tin enolate, which is generated using tin triflate and a base, it will also give me syn aldol, right? So I hope I have covered all the important part of this aldol condensation in this video, and if you have any doubt you can ask me. And if you like my videos, please share my videos with your friends. Thank you so much for watching.